Hello, my name is Hang Lee. Welcome to my talk. Today, I'm going to be talking about optimal approximate distance oracle for planar graph. This is a joint work with Christian Wulff-Nilsen from University of Copenhagen. So let's dive right into the talk. So today, I'm going to be talking about approximate distance oracle. A 1 plus epsilon approximate distance oracle for a planar graph is a data structure that can answer distance query of the following form. Given two vertices x and y, I want to return a number dhy such that dhy is going to be at least the distance between x and y in the graph, and at most 1 plus epsilon times the distance between the two vertices in the graph. So here I had an example graph and two vertices x and y whose distance in the input graph is going to be 2. And when epsilon equal to 1/3, the oracle are allowed to return distance at most 3. And we are interested in the total space, query time, and the construction time of the oracle. And actually in this talk, the construction time is a secondary goal. So our primary goal are going to be the space and query time. And when epsilon equal to 0, we have exact distance oracle. And one of the simplest planar graph going to be tree. And for tree, we know how to construct an exact distance oracle with linear space and constant query time by reducing to query the lowest common ancestor. So the idea is that for each vertex, we're going to store the distance from h to the root r. And then to query distance between x and y, all we need to do is take the distance from h to the root plus the distance from y to the root minus twice times the distance from the lowest common ancestor to the root. And the same construction going to be applicable to directed tree as well. And for this data structure, the model computation we are talking about is a RAM model with word size omega log n bit. And this is the same model that we take for our construction of the distance oracle for planar graph. Now, what we know for the tree inspire the following question, which is, can we construct an exact distance oracle for planar graph or planar directed graph that has bound matching the bound that we know for tree, which is linear space and constant query time. And this is a long-standing open problem, and tremendous progress have been made over the past 20 years. And the closest bound that we get is from the oracle of Petit and Long with order n plus order 1 space and log square plus order 1 query time. But the construction of an oracle with truly linear space and constant query time remain a very challenging problem for exact distance oracle. So maybe the next goal going to be looking at approximate distance oracle. And the question is, can we construct 1 plus epsilon approximate distance oracle for planar graph or planar digraph that have the bound matching the bound that we know for tree, which is linear space and constant query time for any constant epsilon smaller than 1. And for undirected graph, we know a construction of Wulff-Nilsen that has space order n log n square and log n cube query time. So it is close to the bound that we're asking for, but it's still not resolving the question. And for directed graph, there is a construction by Thorov in 2001 that have order n times log n capital N space and log n times capital N query time, where capital N is the upper bound on the H wave. And there is a vast literature on approximate distance oracle for planar graph that we do not have time to go over here. And here's our result, which basically we answer the questions for undirected graph. We construct an oracle with linear space and constant query time. And for a directed graph, we had an oracle with n times little o of log n times capital N space and order of log n times capital N query time. Basically, we improve the space of the oracle by Thorov by a factor of omega log n while keeping the same query time. And this, even though this is only a log n improvement, but this is the first improvement over 20 years. And for this talk, we focus particularly on undirected planar graph, and our oracle can be constructed in order n polylog n time, but we're not going to be focusing on the construction time here. And There's gonna be hidden dependency on epsilon in the space in query time, and which is a polynomial over 1 over epsilon. But here for the rest of the talk, we assume that epsilon is constant, so we ignore the dependency on epsilon. So in terms of technique, so in our technique, we had 2 steps. The first step is reduction to the construction of an additive oracle with stretch plus epsilon d, where d is the diameter of the graph, and the reduction has order n, space overhead, which is linear, and constant query time overhead. So a little bit more formal, which is somewhat simplified statement, is that if any planar graph with hat n vertices and diameter d, and an oracle with space s of hat n and query time q of hat n, an additive stretch plus epsilon d, then any h-weighted planar graph with n vertices have 1 plus epsilon approximate distance oracle with space order s n plus some linear overhead, and query time going to be qn plus some constant overhead. And the precise statement involve oracle for subset of vertices. To make things simple, we just state a simplified theorem here. In the second step, we construct an additive distant oracle with stretch plus epsilon d, linear space, and constant query time. And this is a little bit more formal statement. Okay, so here are a couple of remarks that I want to make. The 2-step technique was introduced implicitly in the paper of Kawarabayashi, Sommer, and Thoroff in Soda 2013. In the first step, their construction have order n log n space overhead, which is much larger than we need. We want linear space, and they have constant query time overhead. And in second step, they construct an additive distant oracle with n times log star n space and order log star n query time. And for the first step, we bring insight from geometric distant oracle literature to improve the space overhead all the way to linear. And for the second step, we use the power of RAM to get rid of the 2 log star factor. Basically, we get linear space and constant query time. Okay, so let's first look at the second step, which is somewhat simpler than the first step. So the input going to be a planar graph with diameter d, and we want an oracle with stretch plus epsilon d, linear space, and constant query time. And the main tool that we use is Schwarzschild separator, which is implicit from the paper of Lipton and Chajan. And the Schwarzschild separator is the following. We said that a planar graph can be separated by a simple cycle, which compose of 2 Schwarzschild paths and plus 1 edge, such that each side of the cycle has at most 2/3 number of vertices. And here's the idea of using the Schwarzschild separator to construct an additive distant oracle. The basic idea, we place order 1 over epsilon portal p along the Schwarzschild path of the separator, so that the distance between any 2 nearby portal is going to be epsilon d. Okay, and for each vertex, we're going to store the distance from u to each portal, and the total space is going to be order n over epsilon. And if u and v are in different sides of C, then we can return in constant time the estimate distance, which is going to be minimum over all the portal, the distance from u to a portal, plus the distance from v to a portal. And we call this distance by portal query. And we can show that if u and v are in different sides, then the estimated distance is going to be within plus epsilon d of the true distance. Now, what happens if u and v are in the same side? Well, we can recur on each side of C to handle distant query of vertices on the same side. But the catch is that the recursion is going to have log n depth. And for each vertex, we must store distances from u to the portal of log n subgraph, so that the total space is going to be n, which is the number of vertices, time order 1 over epsilon, which is the number of portal per subgraph, and log n going to be number of subgraph. So we have something like order n log n, which is too much because we want linear. So the idea we have is early termination. Basically, we terminate the recursive when the subgraph have size log n. And now for each leaf piece, which is a leaf subgraph, we store the distance from the portal of P, like all the portal here, to all the portal of the ancestor. So the total space is going to be the number of leaf peas, which is n over log n, because we terminated early, times order 1 over epsilon, which is number of portal that a piece have, plus log n over epsilon, which is the number of portal of all the ancestor subgraph, which gave us something like linear. And so to answer distance between U and V in 2 different pieces, like from U in this piece and V in this piece, we first go from U to some portal, and then from V to some portal, and then query the distance between 2 portal using this recursive structure. And we can guarantee that the distance is going to be within order 1 plus epsilon d, order epsilon d. And this can be done in constant time. Now, what happened if the 2 vertices and the same P? Well, we're going to recursively decompose the piece by applying the same reduction until a smaller piece now have a log n of the input, which is log n. And because the piece now have a log n size, we can store all the pairwise distances in a single machine word, which have a size omega log n. And so that the distance query between vertices in the same leaf P can be done in constant time by the table lookup. And for distance query between vertices in different pieces, we can use the recursive structure that can be done in constant time. So this is the basic idea of the construction for the second step, which is an additive distance oracle with linear space and constant query time. Now, we focus on the first step, which is a reduction from multiplicative strat to additive strat with linear space overhead and constant query time overhead. And the tool we use is nettree plus Sparse cover. And to make the presentation simpler, we assume that the market distance over the mean distance is going to be polynomial in the number of vertices. And we show how to remove this assumption in our paper using the power of RAM. So the basic idea is using the net tree. So what is a net tree? Well, it is a tree where the leaf of the tree contains the vertex set, and higher level going to be subset of the lower level. And we have log n level because the maximum distance over minimum distance is going to be polynomial. And for each level I, we have to the power of I net. And what it means is that for each vertex h at level I and h of its children u, we're going to have distance from u to h of at most 2 to the power of I. And then for any 2 vertices at the same level, we have the distance between x and y is at least 2 to the power of I. And we can show that the net tree in the worst case have a size omega n log n because of degree 2 vertices. And so we can reduce to size linear by compressing all the degree 2 vertices. And by compressing, I mean delete the vertex and then connect the parent to the children. But here we could not simply compress all degree 2 vertices because we need some of them for the distance query. So what we compress is that for every degree 2 vertex, if we look at the ball of radius 2 to the power of I over epsilon, if it doesn't contain any other vertex in the same level, then we compress it. It might contain vertices at the lower level, but here we only care about whether it contains a vertex in the same level or not, other than itself, other than the center of the ball. And we can show that the size of the compressed net tree going to be order n times log 1 over epsilon, which you an amortized argument to show. You can refer to our paper for detail. So now we had a net tree of size roughly linear. And for distance query between u and v, the first step is that I'm going to find the ancestor of u and v at level I, such that their distance is at most 2 to the power I epsilon. So we find a minimum level I such that the distance between the ancestor going to be 2 to the power of I over epsilon. And we can show that the distance between 2 ancestors going to be roughly the same as the distance between 2 vertices. So we can just query the distance between the ancestor rather than querying distance between 2 input vertices directly. Now, to query the distance between ancestors, we need to find the ancestor first. And in the paper, we show how to construct a data structure to find the ancestor with linear space and constant query time. And the rough idea is that this data structure contains 2 smaller data structure. The first is a distance oracle with linear space, constant query time, and constant stretch. And the second data structure is weighted level ancestor. That I would not go into the detail of this construction, but this can be done. Now, given two ancestors, we want to query distance between them, and we do so by constructing distance oracle for each level of the net with linear space in the number of vertices of the net, and with constant query time and stretch 1 plus epsilon. And the total space is going to be the size of the tree, which is roughly order n, if we are able to construct such a data structure. Now, to construct distance oracle for the net Ni, remember that we're only interested in the pair ICU and HV where the distance is almost 2 to the power I over epsilon. And by definition, we have the distance between ICU and HV going to be at least 2 to the power I. And the way we design such kind of data structure is using Sparse cover and the additive distance oracle that we construct in the second step. So let me give you the rough idea of Sparse cover. I do not try to give you a precise statement, but that is the final puzzle piece that we need. So basic idea is the following. Given a graph, we can cover it by a collection of clusters that have the following property. Each vertex belongs to a more constant number of clusters of diameter d, which is order of 2 to the power I over epsilon. And for every ICU and HV, where the distance between them is at most 2 to the power I over epsilon, then there exists a cluster that contains every vertex on the shortest path from ICU to HV in G. So see this cluster here, gonna contain every vertex on the shortest path from ICU to HV in the graph G. And so to query distance between U and V, it's suffice to query distance between U and ICU and HV in the cluster C. And we do so by constructing an additive distance oracle for C with stretch epsilon square times D, where D is a parameter here. And we can show that the result returned by the additive oracle going to be roughly 1 plus epsilon times the true distance between ICU and HV. This is not very difficult to show, but this is something we can show by the definition of the set Ni and the fact that this is at least 2 to the power of I. And in terms of space, we know that because each vertex belongs to only a constant number of clusters, so there's a total space of the oracle for Ni going to be the total space of the oracle for each cluster, which is linear on the number of vertices of Ni in the cluster. And that we get, linear space because each vertex belongs to a constant number of cluster, and the query time is constant because the additive oracle have query time constant. So that is a rough idea of the reduction to constructing an additive oracle, and that is the two-step here is the idea of the construction of our oracle. So open problem, I have two open problems. The first open problem is, can we construct an approximate distance oracle for a directed planar graph with linear space, constant query time, and 1 plus epsilon stretch? So our result is n times little over log capital N times n space and order log n times capital N query time. Okay, so can we get rid of these factors? The second question, which is more ambitious, is to construct an exact distance oracle with linear space and constant query time. And this is going to be a very interesting problem. Thank you.